Hello and welcome to the lecture Convolutional Neural Network Part 2. Today we'll discuss model architectures. In this lecture we are going to cover different CNN architectures like LayNet, AlexNet, VGGNet, GoogleNet, etc. We start with LayNet. LayNet basically introduced long back since 1998 by LeCun and colleagues. It is one of the earliest successful convolution neural network basically made for handwritten digit recognition. Now, in this particular LayNet, the most well-known version was LayNet 5 that basically consists of 7 trainable layers. First layers input layers accept 30 cross to 32 input graphical image, and then followed by 2 convolution layers C1 and C3 that extract local image features using learnable filters. And then the other layers come. Particularly these convolution layers is followed by an average pooling S2 and S4 in C1, S2 and C3, S4, which reduce the spatial dimension and improve. So that is basically this convolution, then sub something, again convolution, something. Okay. So these are the very generic or very simple kind of convolution network. And then after feature extraction up to this, there is a fully connected network C5 and followed by another fully connected layer F6. Okay. And then the output layer, which is basically going to have 10 different classes of 10 different digits, 0 to 9 or something like that. Now, LayNet generally employs sigmoidal nonlinearity or tanh nonlinearity as activation function and backpropagation used for the training. Okay. So the main feature here, as you mentioned in case of when we discussing the generic convolution neural network, that hierarchical feature learning. So different features are learned at different level of abstraction at different hidden layers from the initial layer to the deeper layers. Different layers learn the different kind. Kind means different level of abstraction of features. Through convolution and pooling could achieve a high accuracy and will reducing the number of trainable parameters. That is the major thing that basically this kind of network process. And LayNet not that much deeper, but it's a foundational model that inspired the modern deep convolutional neural networks. The architecture is very similar, okay, not very deep. Basically, in long back for very deep model, there is no algorithm suitable for training. As we have understood that vanishing gradient problem, other problem may create some problem. That we'll see in these successive lectures or subsequent lectures, that how we get rid of this. Okay. So this is LayNet. It's a very old but kind of foundational model. Next, before we go to the next model, we want to introduce one concept that is called padding. Now, padding is a concept that is very frequently come in this deeper neural network like CNN. That means this process adding extra pixel, typically zeros kind. Now, when it is really come into the picture, let there is a one image patch and another a convolution kernel. So convolution kernel is basically first this particular middle part or center part of this cursor. First put it here. Now if this part is put it here, so this it will create this kind of thing. So these here, this part is image is basically there is no image patch or image pixel in these positions. So we put 0 here. It's called zero padding. Okay. So adding extra pixel, typically zeros, around the border of the input image or feature map before applying convolution. So this is basically the zero padding. So if you put it here, so it come here, 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 and it will get this kind of zeros. So it is called zero padding. It prevents rapid reduction in spatial dimension and preserve important information in the image boundaries. That is called padding, and it's an important concept will require our understanding of this payment. The next important convolutional neural network is AlexNet. AlexNet is basically the first landmark deep convolution neural network which win this competition at ImageNet Large Scale Visual Recognition Challenge ILSVRC. AlexNet is proposed by Kuchervsky and Hinton et al. In 2012, and in this particular network there were 8 learnable layers, okay, including 5 convolution layers followed by 3 fully connected layers. Most importantly, since it is ILSVRC challenge, it has 1000 outputs, so softmax based output layer for classification. It's a huge network. So in that time, due to some hardware resource, this architecture being trained in 2 GPUs. Okay. Now in this illustration of the architecture, though it is showing the that explicitly showing the delineation of responsibilities between 2 GPUs. That means the total architecture is so huge. In a single GPU, it can't be trained. So 2 GPUs is used. One GPU runs the layer parts of the top of the figure, as we have seen here, and other GPUs runs layer parts at the bottom. And for some here, the GPU communicates certain layers communicate. So that's why this is the actual architecture was given in the paper, source paper, this very phenomenal work. And you can say that AlexNet is the first deep learning based architecture that won this challenge in 2012, and the era began. Okay. Now, this network takes as an input This is an image patch up to 27 by 227 into 3. These are RGB images. That's why these three layers are red, green, blue, and introduce a several key innovation thing. That means this AlexNet introduced several things or several key innovations. First up, this RLU, that means rectified linear unit, has been used in place of sigmoid or tonnage for faster training, because this is faster, and it's somewhat helpful for handling the vanishing gradient problem. Then overlapping max pooling layers for spatial downsampling, that is also been introduced here. Dropout in the fully connection layers is introduced to reduce the overfitting. And data augmentation technique, because it's a huge data set is required. Augmentation techniques such as image translation, horizontal flipping, and have been used to improve the generalization. So we can see there is a quite few key innovations that have been introduced by this AlexNet neural net. It was trained using SGD, that means stochastic gradient descent. Now here I just want to take 1 minute to what is stochastic gradient descent. Normal gradient descent, sometimes called batch gradient descent, it is very accurate, but the problem is that it's if number of samples, that means in a batch there's a huge number of samples, then it is computational complexity is very high. It's very easy to understand because for all these samples we have to calculate the gradient using the chain rules and all this. Stochastic gradient descent in that case is much more faster, that it randomly choose a single sample out of the whole batch, and then it used basically the gradient error and this whole backpropagation thing with this randomly chosen sample. So one thing it is that it makes the converging path is bit random, but since specifically when the number of sample is very high, then it substantially reduce the computational complexity of the gradient descent development. So that is being used here on GPUs, which enable efficient optimization of its approximately 60 million parameters. You can understand 60 million parameters, so it's a huge. So it achieved a substantial reduction in image classification error. It demonstrated its effectiveness on deep learning for computer vision and laid a foundation for subsequent very popular architecture like VGGNet, GoogleNet, ResNet, and so on. So this is as a whole the AlexNet architecture, which is the first and one of the you can say that very successful in this era of deep learning for the computer vision task. Now here some recollection of our concept. For that reason, that as we see that our input is 20 to 27 cross to 27 into 3, the first year convolution. Now 96 convolutional filter of size 11 cross 11 is used, applied with stride 4. Now the question is, what will be the output volume or output size after this first convolution layer? Now we recall that this f minus n, that 227 minus 11 by number of stride by 4 plus 1, so it's a 55. So output volume 50 cross 5 cross 55, and such 96 convolution filter, so channel become 96. So 55 cross 55, 96. So this is the output volume. Next thing is that what is the total number of parameter? You see, 11 cross 11 is the convolution parameter into 3, since it is a 3 channel, and such 96 different kernels. So 35,000 parameters in this single convolution layer. So that is, you can understand, it's a huge, it's a very big network here. Okay. Now, one thing and you understand, this is the first CNN based VNet in 2000, that is AlexNet. Okay, in 2012, what we have seen here. Then several, this BGG come to 2014, even Google Net come to 2014, ResNet in come to 2015, so on. We'll discuss one by one. So this is one of the major, and you can see here also that how the error, top 5 error is reduced, a substantial reduction from the shallow end. Okay. And then more deeper layer it will come, and in next slides we'll discuss this VGG net, Google net, etc. Our next very popular convolutional neural network is called VGG net. VGG net is basically a particular neural network which has a increased network depth and a simple and uniform design. In 2014, Karen Simonian and Andrew Schumann in Oxford, they proposed this deep convolution neural network architecture for image classification challenge. So in this network, this, what is the major, you can say, the innovation is that this depth of the network and a very simplistic design. We'll see how this depth matters in subsequent slide. Two major variants of this network, which is 16 and 19. Here we have shown the VGG 16. In subsequent slide we show 19 also. VGG 16 contains 16 learnable layers and VGG 19 contains 19 learnable layers. And this is the concept, the multiple convolution layer, that it is very interesting design style, that multiple consecutive convolutional layer is placed with stride 1, and then the 2 by 2 max pool layer. Okay. So one important thing that we're going to understand here, that this kind of style, that is multiple 3x3 convolution layers with a stride 1 and padding to preserve the spatial dimension, what it means actually. That is one of the important innovation and architectural design, or you can say architectural masterpiece, that really make this paper a milestone paper. Okay. Now, this network accept 224 cross 224 RGB, that means 224 cross 223 images as input, and concludes with 3 fully connected layers, as you can see here. This is VGG 19 and 16. Okay, but the final layer uses softmax classifier for the output prediction. So what we can see, that apart from this very interesting design of multiple convolutional layer, and this architecture is a very simplistic architecture, and depth is bit high or higher than the previous architectures like AlexNet, etc. And then they use the fully connected layers, and finally the softmax classifier for output. Here also the value activation function is used, and this enables efficient training and input convergence, as we have seen or discussed in the previous slides. Now, what we have said, the deeper networks with small convolutional filters, that is the one of the main important feature of VGG net. This achieves a superior recognition accuracy. And 2014 it is the winner of this challenge, this ImageNet challenge, and become a widely adopted feature extra. And another important thing we have observed in the literature, that so many variants or so many work is depends on used this architecture, and that will become benchmark architecture for numerous computer vision applications. So VGGNet is very popular in that sense, mainly for downstream vision task, but it has some disadvantage, that it relatively high computational cost, because it can easily understandable that it is a very in the depth or deep network. This is 19, this is 16, and large number of parameters. So this is altogether the very introductory description of VGGNet. Now we have to understand that why this kind of architecture is helpful. Okay, multiple convolution layer, 3x3 convolution layer is accessible if we this setting, how it helps. To understand this, that we have to understand the key design principle of the VGGNet. Use of stacked 3x3 convolution layers. That will help. instead of a larger convolutional filters. And that's very interesting. That we'll see specifically three consecutive 3x3 convolution layers with a stride 1 provide a same receptive field or same effective receptive field as a single 7x7 convolution. Now, allowing the network to capture equivalent spatial context while using a more efficient approach. Now, here you can say using such 3x3 at in a stack of three convolution layers. Since it is a three separate layers, that it increase the nonlinearity. Each 3x3 convolution is followed by a ReLU activation function. So stacking three such layers introduce three nonlinear transformation instead of one, enabling the network to learn more complex hierarchical and discriminative feature presentation. That is a very interesting and important point, because each convolution layer is followed by ReLU. So if we use only one single 7x7 convolution, the one value is activation and was imposed. Rather, here we use the three activation. Second, we'll show there will be a parameter reduction. So parameter efficiency, replacing a 7x7 with 3x3 convolution significantly reduce the number of trainable parameters. So these two very important things. It looks very simple, but this is a very interesting and advantageous for the deeper network design. Okay. Now we are trying to understand why stack of 3x3 convolution with stride 1 layers has same effective receptive field as 1 7x7 convolution. Now let these three, we have a three different color for three different kinds, and we put a stack of three. So first we convolve this with this convolution there. If we do this, that as per our previous understanding of padding, we get a convolution layer like this, the 5x5 convolution layer. Now if this is the 5x5 convolution, again we convolve with another 3x3, then it's basically a 7x7 convolution. So effectively, the receptive field of this 3x3 convolution layer in a stacked manner, in a sequence, it results a 7x7 receptive field or effective receptive field, and that is the major advantage of this network. So this 7x7 convolution layers 49 parameters per input-output channel pair, whereas 3x3 convolution layer require only 27 parameters, reducing both computational cost and risks of overfitting while maintaining the same receptive field. So here what we can say, we can get the same receptive field but with less parameters. So this combination of deeper feature extraction and enhance the representation means expressive power, and it is input parameter efficiency is a fundamental reason the VGG made strong performance in image classification task. So that is very important to understand. So this is the similar question, same question. Why use a smaller filter in a stack? So stack of three same effectiveness. Now that what we have seen, we sum it with in a summary. You can say we use a stacked 3 cos 3 single 7 cos 7 convolution. This stacked 3 cos 3 versus single 7 cos 7. Reciprocal equivalence is the same because both are 7. But benefit 1 for 3 cos 3, stacked 3 cos 3, increased nonlinearity that we have seen before. The stacked architecture is deeper and improved, incorporates the 3 nonlinear activation layer instead of 1 for 1 7 cross 7, enabling the network to learn more complex and discriminant features. And second efficiency is the parameter reduction. The stacked 3 cross 3 layer uses significantly fewer parameters. If there is a C number of channels, the stacked 3 cross 3 is 27 cos 3 square, where a single 7 cos 3 is 49 square. So 45% parameter reduction here for this VGG architecture. So finally, if we see that a one module of VGG16 or in this is basically using this kind of input is 224 cross 224 into 3. Memory required is almost 150 kilo, that means, and parameter is 0 here because it's input layer. So 150, this memory size k means 150,000. So convolution, first convolution is 3 cos 3, 64 such convolution layers, this, and 24 into 64 is basically the output volume. Memory is 3.2 million and parameter is 1728. This is the first convolution layer. Second convolution layer is another 64 different convolutions. So 224 to 64. Then memory is 3.2 megabyte and this parameter is 36,864. Pooling layer is 2 cos 2. So it downsampled 112 into 112 into 64. Memory is 800K and parameter is 65. So this is just a idea that how one such modules requires resources. Okay. And this is the most about VGGNet. So what we have seen, VGGNet can reduce the top 5 error rate from 11.7 to 7.3. It is a 19-layer VGGNet in 2014. Okay, in the next, we'll see what is GoogleNet. Same year it came, and again it lowered down this. It is 22nd layers net, how it can do it. Next, we discuss GoogleNet. GoogleNet, this introduced by Christian Sezdi and his colleagues in 2015 by Google. So GoogleNet is basically a deep convolution neural network, and it owned the ImageNet large-scale visual recognition challenge. That is we discussed in last few slides. That ILS VRC 2014. By combining the high classification accuracy with less computational cost, it tops this challenge, ILS VRC 2014 classification challenge. It is 6.5% top error rate. So what we can understand that GoogleNet become the top deep neural network in 2014. It owned this challenge that year. So before we going to understand what is the GoogleNet is, that we have to, what is the basic purpose of these challenges, that is image recognition challenge. There is some image processing issues, and whatever these CNN we are discussing at this moment, these CNNs are basically made for the spatial digital signals like images. And not only that, this image recognition task, that these networks are basically very much specific to this task. This architecture, GoogleNet architecture, consists of 22 learnable layers and built around a novel inception module. Why I said this? Because in GoogleNet there is some innovation that is very relevant to the image processing or computer vision task, specifically recognition task. So one of the key innovation is this inception module for GoogleNet, which processes the input feature through multiple parallel branches, 1x1, 3x3, 5x convolution filters, along with 3x3 max pooling branch. Now, question arises here. Why I said that why it is much more effective for image recognition. Now you see, there is a multiple filters or filters with multiple receptive weights. Now why it is important? Even it is 1x1, 3x3, 5x5, even higher receptive weights sometimes used for image recognition, not for GoogleNet, for other thing. Now, one thing that I assume that you can recall, that given an image, the image statistics are very coherent or homogeneous in a local neighborhood, rather the whole image. The whole image, you can say there is a different type of image statistics present. If there is a kind of scene, a natural scene, there may be a kind of sky, there may be some river, some trees. Okay, now skies are basically a very homogeneous, the background is homogeneous. So there, if there is some trees, that there may be some kind of leaf, branches, so there is some kind of randomness, or if you say in bit frequency point of view, it's a high frequency component, bit high. But when the homogeneous background like sky, fields, like this, then this homogeneity, so there is a low frequency components are basically dominating. So given this kind of statistics, and this kind of statistics are very coherent or in a local position rather the whole image, we cannot expect that a similar kind of statistics are present all over the image. Okay. So one important thing to understand here, that if there is a low order or low frequency elements like a homogeneous background, then the kernel should be bit higher. Let's say 10 by 10 or more than that, 16 cos 16, 30 cos 32, something like that. But if there is a high frequency component, let's say there is a kind of trees, kind of very sharp textures where the high frequency component is dominating, there the lower receptive field is much more easy or much suitable. So this is the basic image processing characteristics, and these networks, always keep in mind this, because these are basically built for this image recognition task. Okay, so if you think from this point of view, it will help for your understanding. So why? Because there is a architecture given, researchers are basically think something to build architecture. When you try to learn that, there may be some question in your mind that why these architectural, is it a kind of trial and error? Not always. There is some reason behind this, and this is some reasons. Now, for this inception module, that is a process the input feature through the multiple parallel branches like this. The output of these parallel operations are concatenated to capture the visual information at multiple spatial scales simultaneously. Now, even this, that term, the multiple spatial scales, what do you mean by that, and why it matters at all? Multiple spatial scales means this, that the image statistics, what we are going to recognize or try to understand or try to analyze, that may be in a different scale. Sometimes it is a very smaller scale where the high texture or high frequency component is dominating, where it is a some sort of higher scale. So multiple scales matters here. Okay. Anyway, that we'll see in our subsequent slide, and how GoogleNet is going to illustrate, or I want to utilize these concepts. Now, another important aspect of GoogleNet that reduces the computational complexity, because if you use the inception net or inception module, the complexity becomes very high. So to reduce the, GoogleNet employs a 1x1 convolution as a bottleneck layers. Okay, that I will come later very in detail how actually 1x1 convolutions is useful to reduce the complexity. So this bottleneck layer for dimensional reduction before computational expensive 3 cross 3 or 5 cross 5. And if we do this, it significantly decreases the number of parameters. So GoogleNet achieved a 5 million parameters, which is 12 times lower than the AlexNet, and that is an incredible achievement. So the network, this GoogleNet accepts 224 cross 224 into 3 RGB images as input and replace large fully connected layers with global average pooling. And this is also another very important innovation or kind of characteristics of GoogleNet. It doesn't have any fully connected layers, and which greatly reducing the model size and mitigating overfitting. So this is another very important characteristics of GoogleNet. Additionally, auxiliary classifiers are attached to intermediate layers during training to improve gradient propagation and regularization. So some auxiliary classifiers are attached to intermediate layers. So with all this, the key innovations owing to its efficient multi-scale feature extraction, reduced parameter count, and improved training strategy, GoogleNet achieved a state-of-the-art performance while using substantially fewer parameters than earlier deep models, such as AlexNet, VGGNet, etc. And thus it make it milestone paper in the evolution of deep convolution. So this is a kind of introduction. Now we will see what do we mean by inception layer. You can see here that this inception layer or inception module, something like that, this is some previous layer, it is coming and it is 3 cross 3, 5 cross 5 cross 1. These are some parallel filters and it is concatenated and to get this to the next output layer. So as a whole, this is the inception module, and these inception modules are basically repeating in a different layers of GoogleNet to get this the actual this thing, the total model. So this is the basic idea of GoogleNet, that will try to understand what is inception layer or inception module, and keep repeating this inception module. We get the GoogleNet as a whole architecture. Okay. So inception module, if we see here, that it is a core architectural building block. GoogleNet is inception v1 version 1 to improve the representational power while maintaining the computational efficiency. Now, representational power means expressiveness, that how well it model the image or a particular statistics, but they always keep in mind the computational efficiency. So previous layer, from previous layer it is coming, it is first coming for 1-to-1 convolution layers. Now why these convolution layers will come later, that is a bottleneck kind of thing. And then main idea is basically this, it's a parallel things, 3 cross 3, 5 cross 5, these are parallel with 1 cross 1, and then concatenate. So one thing we understand here, that this concatenation only have a 3 cross 3 is 5 cross 5 and 1 cross 1. So multiple spatial scales are being concatenated. Rather a single scale, and that is important, and that makes the difference. Okay. So instead of applying a single convolution filter size, an inception module performs parallel feature extraction using these convolution kernels and because the maximum function. And these outputs are basically concatenated along the channel dimension, enabling the network to capture multi-scale spatial feature. That is important. That I just want the last slide within the same layer. That is very important. So this is the basic architecture. This is a naive inception. But what is the problem with this? Okay. Now the problem with this naive design is that the computational complexity. So input from the previous layer is this. Number of filters 128. Number of filters is 192. Number of filters 96 and so on. And in normal case, what will it's directly to come 3 cross 3 convolution, 5 cross 5 convolution, or 1 cross 1 convolution, and is equaling this. And resultant, it's basically the filter concatenation. And module input become this. Now the question comes, what is the problem? What is the output size of the all different? So 1 cross 1 convolution, it is, since it's a 128 filter, if it is a 28 cross 28 input is coming, it is 28 and 28, 128. If the number of filters 192, this 3 cross 3 it is coming. It is 28 cross 20 is 192. It is number of 96, 28 cross 20, 96. And 3 of 3 max pooling, if 20 is going to 56. If we adjoin or fill concatenate, then it will be a very high number. A pooling layer is also preserved feature depth, which means total depth after concatenation can only go at every layer. And total number of operations also you can see 28 into 28, 22, 1 into 256. 1 into 1 convolution. That is 28 con 20 to 192. 3 cos 10 to 256. Because it is a 3 cos 3 filters. 28 cos 20 96 into 5 cross 5 into 256. Because basically this. So total 854 million operations. So what is the output size of the filter? Concatenation. 20 square 28 plus 128 plus 192 plus 96 plus 256. 28 into 26. It is also a very big number. So this is a very expensive or computation point of view. And that is the major problem of this. And here comes the concept of bottleneck layers. So what the bottleneck to reduce this computational cost? 1 cross 1 convolutions are strategically used as well. Before the computational expense is 3 cross 3 of them. significantly decreasing the number of input channels and reducing the parameters and plotting parameters. Now, this is the kind of channel. 6 cross 6 is spatial and 32 channels. So, if there is a 1 cross 1 convolution, there will be 32 channels. What will be these feature maps? It's 6 cross 6 because this for each 6 cross 6, it is only one value. So a bottleneck layer in a convolutional neural network is a low dimensional intermediate layer that reduces the computational cost and the number of parameters by compressing the input feature maps. It is typically implemented by one-by-one convolution to reduce the channel depth before the more computationally expensive operation. As we have seen, this 1 cross 1 is 32, and for this, if only one, this is the just element-wise multiplication. That is. Now, how it helps for this? This what we have seen before, that this is a 32 channel 6 cross 6 image and 1 cross 1 kernel of 32 channel got 66. By what? By this 32 channel, it will come here. Pixel values from each 32 channels are multiplied with corresponding convolution kernel coefficient and are series sum to get the 1 pixel response matrix. In such a way, we can get a 6 by 6. This is the way. Now, if such 4 filters be used, we get 4 different feature maps, each of which has 60 cos 6 by 6 this size. So you can see number of filters here is basically give you the channels by this means of 1 cross 1 convolution. So what does 1 cross 1 convolution do? Is a 1 cross convolution used to reduce the channel dimensionality of feature maps without altering their spatial dimension. So height which is same, it was in PS 192. Now if we use the 1 by 1 is 192 filters and such 32 filters, it becomes 20 cross 20. That it is substantially reduced with such 192 channel dimension. And that is the basic idea of bottleneck layers. So this concept basically used by GoogleNet. GoogleNet stacks multiple inception modules hierarchically, allowing the network to learn increasingly abstract and scalable features, as we have discussed before. And to reduce the computational cost, 1 cross 1 convolutions are strategically used as a bottleneck layer. Prefer the computationally expensive 3 cross 3 5 cross convolution because this is bottleneck layer, because this is a bottleneck layer. Significantly decrease the number of input channels, reducing the parameters and plotted product. And this design addresses the trade-off between network width and computational complexity while preserving the expressive capacity or representational capacity of the network. So that is the basic innovation, the key innovation by GoogleNet is this inception module where we can concatenate the multiple scales feature, but without much computational cost using the concept of bottleneck layer. And that is a very interesting and very, you can say, big innovation here. So, if you say additionally, some in the architecture is called auxiliary classifier like this during the training to improve the gradient propagation and mitigate the vanishing gradient problem that we understand. So as a result, Google and achieved a state-of-art performance on ImageNet benchmark with substantially fewer parameters than the earlier deep convolution layers, demonstrating the sparse approximation can be efficiently implemented using a dense convolution operations. And that is the major idea of net. Okay. So here you can see that if you see that how much operations is required for one by one convolution, these are the some details. Some parallel branches as naive inception layer used for 1,64, that we already been given. That similar kind of effect we have used, and it's become 358 million operations. So if you compare with the naive one, it was naive one is 854 that we have discussed, and now it become much much smaller, that 358 kind of ops after pulling there. So this is the one of the uh, basic advantage of reducing the computational cost by using the bottleneck layers. Okay. So in summary, in this lecture, we basically describe different CNN architecture. We start with LeNet, then we discuss one by one AlexNet, VGGNet, and GoogleNet. In the next lecture, we going to basically CNN optimization, where we'll see how the vanishing gradient problem can be handled in this deeper network. Thank you very much.